welcome to my talk. I know it's almost time for lunch. Thank you for staying with me for the next 15 minutes. So today I'm going to talk about streaming from Iceberg data lake. We all want to build data pipelines that have low latency, are cost-effective, and easy to operate. Today I'm going to show you how to achieve those goals by using Apache Iceberg as a streaming source. I'll first give a quick introduction about Apache Iceberg and Apache Flink. Then we'll look at some of the motivation why we're thinking about using Apache Iceberg as a streaming source. Next, we'll talk about high-level design of the Iceberg streaming source and some of the benefits it brings in. After that, we're going to dive deeper into the Flink watermark alignment and how it works in the Iceberg streaming source. And finally, we're going to look at the evaluation results. Apache Iceberg is an open table format for huge analytic datasets. What is the table format? You might be familiar with the file format like Apache Parquet. It's about organized records within a data file. Table format like Apache Iceberg is about organized data files within a table. Apache Iceberg was designed to address the correctness and performance issue of the old Hive table format. Iceberg brings numerous benefits. First, it provides serializable isolation. All table changes are atomic. Readers will never see partial or uncommitted data. Iceberg supports fast scan planning with advanced filtering using partitions and column-level statistics. Iceberg supports safe schema and partition evolution. It supports time travel, which enables reproducible query using the exact same snapshot in the Iceberg table. Recently, Iceberg added a feature like branching and tagging. With branching, we can implement write, auditor, and publish pattern. We can write new data to a staging branch first, run the data validation. Once the validation passed, we can merge the staging branch to the main chunk. So you can manage the data as a code, like you're familiar with the GitHub Git workflow. So where does Apache Iceberg fit in the big data ecosystem? At the bottom level, we have the data files like Parquet or org. They're stored on distributed file system like HDFS or cloud storage like S3. Then we have table format like Apache Iceberg, Delta Lake, or Apache Hudi. They provide the SQL table semantics. Table format is all about metadata management. And compute engines like Apache Flink, Apache Spark, Trino, they integrate with the table format to access underlying data files. Apache Flink is a distributed stream processing engine. It is one of the most popular stream processing engines. It is highly scalable. A single Flink job can process trillions of events per day. It can run on thousands of cores and maintains terabytes of state in a single Flink job. Flink checkpoint provides strong state consistency or exact once processing semantics. If the sink also supports transaction write, like Iceberg, we can achieve end-to-end exact once also. Flink supports event time processing semantics. It uses a watermark to reason about event time progress within the application. Watermark also provides a flexible way to trade off between the completeness and the latency of the results. Flink provides a layered API from low-level data stream API to a high-level table API and SQL. Next, I'm going to explain why we're thinking about Iceberg as a streaming source. Here, the data pipeline you might be familiar with. Where device send the raw events to an edge API services will then ingest the raw data into a Kafka message queue. This ingest delay is typically very fast, like seconds or less. Then we have stream processing engines like Flink, read data from Kafka and write raw event to a data lake like Iceberg. After that, it's mostly batch jobs for ETL, feature engineering, and maybe offline model training. those batch jobs are typically scheduled hourly or daily. So the overall latency is at least a few hours, if not days. We know latency matters for machine learning pipelines. The industry is increasingly shifting toward real-time machine learning for online learning and online inference. So how can we reduce the latency of our data pipeline? Kafka is probably the most popular streaming storage for Flink. It can achieve sub-second read latency. So if you care about latency, why don't we switch everything to Kafka and Flink? Right. There are pipelines built that way. Kafka is a fantastic streaming storage. I love Kafka. It can achieve sub-second read latency, which is great if you have really low latency requirement. But as we know, system design is all about trade-offs. Nobody is good at everything. There are a few things in Kafka that's not very pleasant to work with. If you operate a stateful storage system, you know it's not easy. System upgrade can be painful, and because we cannot difficult to auto-scale a stateful storage system, so we have to do careful capacity planning, and we have to worry about the burst backfill workload, and how to achieve isolation so that the bursty backfill workload does not affect the live traffic. In a Flink meetup, Storm from Netflix demonstrated it's 38 times more expensive to store long-term data in Kafka compared to Iceberg. Kafka also recently introduced the tier storage within the Kafka that can help reduce difference, but it won't be completely able to completely bridge the gap. So that's why many companies adopt the practice of tier storage. They use Kafka to store the recent data for the last a few hours or maybe a few days. Then they store the long-term data on the Iceberg data lake. Kafka is used for serving stream processing workload, and Iceberg is used to serve the batch workload. For availability reasons, Kafka brokers are typically placed on different availability zones. That can incur cross-agent network traffic, from producer to broker, or broker to broker for replication, or broker to consumer. I did a back-envelope calculation using public listing pricing for a major cloud provider. My calculation shows that the cross-AZ network cost can be 10 times more expensive compared to the broker cost, compute and storage combined. Kafka do provide a rack-aware partition assignment. It can avoid the cross-AZ traffic from the broker to consumer. But we still have the producer to broker and the broker to broker cross-AZ traffic. That's still pretty significant. Kafka source doesn't provide filtering or projection at the broker side. If we have different consumer jobs, they're interested in different subsets of the data, like by filter or projection. All of them have to pull down the big pipe and apply the filter and projection at the consumer side. This is obviously inefficient. People have been setting up routing jobs just to apply the filter and projection to produce smaller substream, such as all the downstream jobs, they only need to consume the smaller substreams. This definitely helps with improve the efficiency, but also it creates an actual routing job to maintain and the data duplications. In Kafka, a partition is an unbounded stream of records. Kafka source statically assigns the partitions to the workers during the job initialization. This assignment remains static throughout the life cycle of the job unless the topology changes, for example, add a new worker. This leads to a few limitations. First, in production, sometimes we can see outlier worker node whose performance is significantly lower compared to the other peers. In this case, because the partition is an unbounded stream, there's no work sharing or work stealing. Even if other workers they have actual capacity to spare, they cannot pick up the slack. Second, Kafka sort parallelism is limited by the number of Kafka partitions. adding a new worker won't help improve the read throughput because it's not getting a new partition assigned to it. Over-provision the number of Kafka partitions can help alleviate the problem here, but too many partitions does have performance penalty on the broker side and also on the consumer side. Auto-scaling can help improve the cost efficiency and reduce the operation burden. Let's assume initially we have 6 partitions assigned to 3 workers. Each worker gets 2 partitions. We get a well-balanced workload assignment. Now let's say auto-scaling need to decide to scale up the number of workers because the traffic grows. So now it adds a new worker. Now we're assigning 6 partitions to 4 workers. So we get an unbalanced workload assignment. Again, over-provision the number of partitions can help, but it also has performance implications. Those things, this type of thing, is any other alternative streaming storage we can leverage. Next, I'm going to show you the high-level design of the Iceberg streaming source and what the benefit it brings in. As I showed up earlier in the data pipeline graph, we typically have a stream processing engine like Flink, read data from Kafka, write them in data files, and commit the data file to the Iceberg table. Flink Iceberg sync commit the data files after every successful checkpoint in Flink. 1 to 10 minutes commit interval are pretty common. If we commit too frequently, like every second, we're going to create a lot of small files, and also create a lot of metadata files for Iceberg to keep track. Too many metadata files can also stress the Iceberg metadata system. But if we commit too infrequently, like every hour, we can delay the availability of the data to the downstream consumers. So the question we're asking, can a downstream Flink job stream data out of the Iceberg table as they are committed by the upstream job? The answer is yes. Let's say that currently the Iceberg table has snapshot n. The upstream job commits 3 new data files. It will create a new snapshot in Iceberg table called n+1. So Iceberg provides this incremental scan API to discover the new data files appended between 2 snapshots. This is called the incremental scan. Then the Iceberg source will discover the new files, and the readers will read the records from those data files and emit them to the downstream operators. For a streaming job, this cycle continues forever because streaming job, by definition, never finish. It runs forever. So this split discovery cycle continues forever. On the left, I have the code snippet for using construct a Kafka source in Flink. Basically, we set the bootstrap servers and Kafka topics and starting offset strategy. Here I use latest offset and the deserializer. To construct an Iceberg source in Flink, we need to provide table loader. Basically, tell the Iceberg source how to load the Iceberg table from a catalog, like Higher Meta Store or Glue, if you're familiar with. Then we also need to set a starting strategy. Here, I chose starting from the latest snapshot in the Iceberg table, and also monitor interval, how often we want the Iceberg source to discover new data files from the table. Both Kafka and Iceberg source are available in the Flink SQL. This paradigm of streaming from Iceberg works because we observe many streaming use cases, they're actually fine with minutes level latency. They're not looking for sub-second level latency. So with that, we can build low latency data pipelines trained by Flink jobs streaming from Iceberg. We can achieve end-to-end latency maybe in minutes level. In a 2019 Flink Forward presentation, Stephen Irwin put the data processing application in the spectrum of latency. At most real time, we have the transaction processing. They're like the request-response model in a microservice. So latency here is typically milliseconds. Then we have the event-driven application. This problem mostly the Kafka origin comes from. The latency may be the sub-seconds. Then we have streaming analytics, data pipelines, continuous processing, and batch processing. Batch processing that typically scheduled hourly or daily, so that latency is at least hours or days level. Stefan thinks that the four categories in the middle fit the stream processing paradigm. I think this Flink Iceberg stream source fits well for the data pipelines and the continuous processing categories, where the latency expectations are probably in minutes. You may wonder, this seems like a micro-batch model. It is. So how is it different with the incremental batch processing? I think this also related to a question was asked earlier after Sharon's talk. So let me first explain what do I mean by incremental batch processing. It means that we're scheduling the batch runs at a much shorter interval than we typically do, like every a few minutes or even every minute. Because typically this batch job most commonly is hourly or daily. And each batch run processes new files added since the last one. So each batch run will produce a bookmark, tell you where to end, then you discover the incremental data files. As the scheduled interval shortens from hourly or daily to every a few minutes or every minute, the line between streaming and the batch actually becomes blurry. What is the batch? What streaming? Yeah, we probably cannot tell. So what are the limitations of the incremental batch processing compared to the streaming execution we're talking about in this talk? First, as we shorten the scheduling interval to every minute or every couple minutes, it might be more expensive to tear down the job and bring it up again just a few seconds later. We might as well just keep the job running all the time. That is essentially a streaming job, because streaming job runs forever, they never terminate. Second, I have heard from batch users, they are favoring daily scheduling over the hourly scheduling, although hourly scheduling can bring lower latency. The reason is that with hourly scheduling, we can get 24 times more batch runs and higher chance of job failures and the need to backfill. That operation burden pushes them away from the hourly scheduling to the daily scheduling. Now imagine if we're going to schedule the batch runs every minute or every couple minutes, we will get a lot more batch runs and a lot higher chance of job failures and the need to backfill. This operation burden can be too high. Third, most non-trivial data processing involves state. For stateful batch processing, intermediate results are discarded after each run and recomputed in the next run. With stream processing, the intermediate results are stored in Flink state, and they are also checkpoint for fault tolerance purpose. FLIP stands for Flink Improvement Proposal. It's used to describe major new features or public API changes. FLIP 27 introduced a new source interface in Flink. It was designed to address the limitations of the old source function in Flink. The key idea in the FLIP 27 source interface is to separate the work discovery with the actual reading. The enumerator runs on the job manager, which is the coordinator. It is responsible for discover work. The parallel readers runs on the task managers. Those are the worker nodes. They are responsible for actually reading the data from the storage. In FLIP 27, a unit of work is defined as a split. In the Kafka source, a split is a Kafka partition. In Iceberg source, a split is a file, a slice of a large file, or a group of small files. A split can be unbounded, like Kafka source case, or bounded, like Iceberg source. In the Iceberg source, the enumerator will discover split from the Iceberg table and keep track of the pending split in an internal queue. The readers will request a split during the job initialization or when it's done with the current split. So the enumerator will assign a split to the reader. Reader requests one split at a time. It's a pool-based model. FreeRPresen unifies the batch and the streaming sources. The only difference is whether the split discovery is one time for the batch execution or it's periodic for the streaming execution. So what are the benefits of using Iceberg as a streaming source? It ties to some of the pain points we talked about earlier. First, Iceberg can leverage managed cloud storage like S3. It offloads the operation burden to the cloud provider, like for the system upgrade, capacity planning, bursty workload, and isolation. And the cloud storage is also very scalable and cost-effective. This simplifies the storage architecture to a unified storage. Both recent data and the historical data are stored in Iceberg, and Iceberg is used to search both streaming workload and the batch workload. It unifies the live job and the backfill job source to Iceberg. And most cloud blob storage, like S3, don't charge cross-agent network costs within a region. So there's no cross-agent network cost you're seeing earlier. Iceberg source support advanced data pruning while filter and projection. You can provide a filter expression. So the Iceberg scan planning will effectively prune out data files not matching the filter expression. And with projection, the Iceberg source will only deserialize the columns it is interested in, because we use column-oriented file format like Parquet. In the Iceberg source, the split assignment is dynamic. It's pool-based, triggered by the reader. If there's an outlier worker node, it allows other workers to pick up slack because the split is bounded. There's an opportunity for the other workers to steal the work from the outlier worker node. So the other workers, they can just pick up more data files and process them. With Iceberg source, we can typically get a lot more file segments than the number of Kafka partitions. This can bring some operational benefit. For example, with a higher number of file segments, we can support higher parallelism, which can be useful in some cases like backfill. You may want to be able to backfill much faster than the live job, so you want a higher parallelism. With more file segments, you can do that. With a more file segment, it's also more auto-scaling friendly. It's easier to assign the number of the files to the readers in more balanced fashion. We have merged this FreeRPresen Flink Iceberg source into the Apache Iceberg project. It's fully merged, but the only thing I want to call out is that for the streaming read, right now we only support the append-only records. It does not support the CDC read on the updates and the deletes. That need to be addressed in the future. Next, I'm going to dive deeper into the Flink watermark alignment and how it works in the Flink Iceberg source. I want to give a quick recap what is a watermark. In Flink event-based application, records can come out of order. It's necessary to buffer and wait to tolerate the late arrival data. But we cannot wait forever, otherwise the result will be delayed for a long time and the Flink state can grow unboundedly. So at a certain time, we have to stop waiting. That's exactly what watermark is doing. It basically tells us all the data before the watermark have already arrived, so it's okay to emit the result. But occasionally, the watermark could be heuristic, could be wrong. Hence, the watermark is kind of a trade-off between the completeness and the latency of the results. So we talk about watermark, then what is the watermark alignment? Why is it needed? Let's look at the use cases of stateful join. For example, let's say we're joined add impression with add click. For stateful join, we typically need to define join window, which is typically determined by how late data can come. In this case, let's assume we have 6-hour join window. Let's assume everything works well. in a steady state with the live traffic. Let's say we need to replay the two Kafka source to 24 hours ago. Maybe there's outage, or there's some like a data issue. Because those two data streams, they may have different volume data. Let's assume that as impression stream have 4x amount of data compared to the click stream. Because of different data volume, those two Kafka sources, they will proceed at a different pace. In Flink, the pace is measured as a watermark. If we zoom into the Flink job a little bit, it can be simplified as a for operator. It has two Kafka source operators, each read from one Kafka stream. Then we have the co-process function, which does the actual stateful join. This is the stateful operator. Then we have sync operator, which writes the join output to the sync storage. Because the click stream is much smaller, right? So let's assume that source 2 was able to catch up much faster. It was able to catch up with the live traffic, which emits watermark as now. And source 1 was catching up from a much bigger stream, so it will catch up much slower. Let's assume it was emit watermark now minus 18 hours. Because the Flink watermark is calculated the minimal value of all the inputs, so the stateful co-process function will have a watermark at now minus 18 hours. This is the problem. Because the watermark was at one slower in the stateful operator, now it needs to buffer 24 hours of the click stream data versus 6 hours during steady state. This excessive data buffering can lead to performance issue and stability issue for the stateful Flink job. This is actually one of the biggest pain points we experience when running large stateful job in Flink. That's why Flink introduced this watermark alignment strategy in the source. It basically tries to ensure that both sources, they progress at a similar pace. The source 2 will stop reading from Kafka when its local watermark is too far ahead compared to the global watermark. This is the alignment part. This avoids excessive data buffering in the downstream stateful operator. For example, in this case, if we allow 1 hour of maximum watermark drift, then the co-processor operator function only need to buffer 7 hours of click data, which is very close to the steady state. This is how Flink watermark alignment works internally. Let's assume we are 3 readers, each read from one Kafka partition. The Kafka readers extract the watermark from a timestamp field in the record it consumed from Kafka. And they periodically send the local watermark to the enumerator for global aggregations. The enumerator calculates the global watermark as the minimum value of all the reported local watermarks, which would be 1010 in this case. The enumerator then broadcasts the global watermark to all the readers. Then the readers need to check the difference between the local watermark and the global watermark to determine if sorting is needed. Let's assume the max allowed watermark drift is 30 minutes. In this case, reader 0 will stop reading because its local watermark is too far ahead. This is where the alignment part comes in. We need to align the progress of all the source readers. Before I talk about how the watermark alignment works in the Iceberg streaming source, let's recap some of the difference between the Kafka source and the Iceberg source. In Kafka source, the splits are unbounded partitions. In Iceberg source, the splits are bounded data files or file segments. In Kafka source, the split assignment is static during the job initialization. In the Iceberg source, the split assignment is dynamic. It's pool-based from the readers. In Kafka, records are ordered within a partition, first in, first out. In Iceberg source, records may not be sorted by the timestamp field within a data file. In Kafka source case, only readers can extract the watermark information from the records that they read from Kafka. That's the only way. In the Iceberg source, because Iceberg keeps track of column level statistics, like min-max values in the metadata files, the enumerator actually can extract the watermark information from the min-max stats column level statistic in the metadata file without actually downloading or reading the data files. The key idea is the Iceberg source enumerator need to assign the splits ordered by the time. Let's assume the enumerator discovered 9 files, and we order those 9 files by the minimum timestamp value from the column level statistic. Here, the notation means that F1 contains timestamp with records from 9 o'clock to 9:03. Let's assume the enumerator assigned the first 3 files to the first 3 readers, and the readers extract the local watermark by the minimum timestamp value from the data file. So reader 0 will calculate local watermark at 9 o'clock because that's the minimum timestamp value we have from F1. The global watermark is calculated at the minimum of all the local watermark. So the global watermark here will be 9 o'clock. The readers will check the difference between the local watermark and the global watermark to decide if throttling is needed. In this case, all the 3 readers are okay to proceed because they are within the threshold of 10 minutes watermark drift. Let's assume sometime later, reader 2 finishes the data file, so it's requesting a new file and got the F4 back. Now reader 2 will advance its local watermark to 9:13 because that's the minimum timestamp value from F4. But in this case, reader 2 needs to stop reading because its local watermark is too far ahead because the max allowed drift is 10 minutes. So that's the throttling or alignment part. Let's assume sometime later, reader 0 also finishes file and got a new file F5. And reader 0 advances its local watermark to 9:16 because that's a minimum timestamp value from F5. Now reader 0 also needs to stop reading because its local watermark is too far ahead. After some propagation delay, maybe a couple seconds or 2, the global watermark will advance to 9:04 because that's the minimum timestamp value of all the local watermark. Sorry. In this case, the reader 2 can resume reading because its local watermark now is within the threshold when compared to the latest global watermark. So now the reader 2 will resume the normal reading. So the max out orderness we can achieve in the Iceberg source watermark alignment is equal to the max allowed watermark drift plus the max timestamp range in any data files. Let's assume in this case the max timestamp range is from F6, is 8 minutes, and if the max watermark drift allowed is 10 minutes, then we can achieve max out orderness is 18 minutes. So why is it important to keep the max out orderness small? Remember the earlier graph I showed you. When we keep the max out orderness small, we can avoid excessive data buffering in the Flink stateful operator. My colleague Peter Werry is working on the upstream contribution for this watermark alignment in the Flink Iceberg source. This is not fully merged yet. Finally, we're going to look at some of the evaluation results. This is a test pipeline setup. We have a Kafka source job, read data from Kafka and write the same data into an Iceberg table. Then we have Iceberg source job, streaming data from the input Iceberg table and write the same data into output Iceberg table. It's like an Iceberg middle maker. The traffic volume is about 4,000 messages per second, and each message is about 1 kilobyte. The task manager container has 1 CPU and 4 GB memory, so it's a small test setup. What are we evaluating? First, we want to look at the read latency of the Iceberg streaming source, because for streaming job, latency matters. We want to understand that. Second, we want to understand how the upstream commit interval affects the downstream consumption, the bursty consumption in the downstream. Third, we want to compare the CPU utilization between the Kafka source and the Iceberg source. We have measured the latency from the Kafka broker to the Iceberg source processing time. If we zoom into a little bit, there's actually 3 segments. First, we have the Kafka source, Kafka read latency, which typically is very, very fast, like sub-second. Then we have the commit interval, how often the upstream job commits the data file to the Iceberg table. Third segment is the pull interval, how often the Iceberg source pulls the Iceberg table to discover the new data files. So the latency is most determined by the last 2 segments, the commit interval and the pull interval. Here we're going to look at some of the latency histogram with 10 seconds commit interval and 5 seconds pull interval. The x-axis is time, y-axis is latency in milliseconds. We can say the max latency is less than 40 seconds. And the median latency is fluctuated around 10 seconds, which corresponds to the 10 seconds upstream commit interval, which makes sense, right? Because we commit a batch of files and downstream read a batch of files. Because the Iceberg data commit is a global transaction, that can lead to stop-and-go consumption pattern. The top graph shows the CPU usage for the Kafka source job. So the x-axis is time, y-axis is the number of cores it used. Remember, we're using 1-core container. From this graph, we can see the Kafka source job is always busy. It's always pulling data from Kafka, processing them. But if you look at the Iceberg source job, here we're using 5 minutes commit interval and 30-second pull interval. We can see the Iceberg source job was busy, process a batch of files for maybe 2 to 3 minutes. After done with the batch, it was idle for the next 2 minutes maybe. Until the new batch comes in, and it was busy again, then it's idle for the next 2 minutes. This kind of stop-and-go consumption pattern is what we expect out of the global transaction writing in Iceberg. But I want to show you, as we shorten the upstream commit interval and Iceberg source pull interval, the CPU usage can become much smoother for the Iceberg source job. The top graph is from the previous slides, is for 5 minutes commit interval and 30-second pull interval. The middle graph is for 60 seconds commit interval and 10-second pull interval. You can see we don't have those long idle gap of 2 minutes or 3 minutes anymore, although it is still much choppier compared to the Kafka source job. So it's still burstier compared to the Kafka source. But as we further shorten the schedule interval to 10 seconds commit interval and 5-second pull interval, we probably cannot see much difference in terms of CPU usage between the Iceberg source job and the Kafka source job. The pattern maybe looks very similar. Finally, we're going to compare the CPU usage between the Kafka source job and the Iceberg source job. We're going to say the only difference between those 2 jobs is in the streaming source. One is the Kafka, the other one is the Iceberg. Everything else actually pretty much the same. Here the CPU usage comparison between the Kafka source job and the Iceberg source job. We apply smooth function so that the CPU usage does not look so choppy, so it's easier to read the overall trend. We can say the Kafka source job has CPU utilization at 60%. Iceberg source job has CPU utilization at 36%. I know benchmark is tricky. I think the main takeaway is that Iceberg source job is as performant as the Kafka source, streaming source, if not better. I want to close my presentation with the next slides. If any takeaway, this is the next one. We can build the low latency data pipelines chained by Flink job streaming from Iceberg. We can achieve overall latency in minutes level. They're cost effective and they're also operation friendly. Thank you. I think the question was, for people coming from like a batch background, is there like a difference for like a different computer engine like a Flink or Spark? Do they work better with one data lake solution like Iceberg or Hoodie or Delta Lake. I think initially, for example, the Iceberg was coming from the batch analytic data set background, and the Hoodie was coming from the stream use cases. So that's why I think Hoodie probably have better support for the CDC read or those types of things. But last couple of years, we can see some convergence on those like data lake solutions. They also try to learn from each other, trying to kind of address the weakness in its own system. So I think all the common data lake solutions like Iceberg, Delta Lake, Hoodie, now they are all pretty much a very good integration with all the popular engines like Flink, Spark, Trino. So yeah, I don't think I would say there's a significance of one is working better with the other. Yeah. So sometimes depend on what kind of technology you are familiar with or you're more comfortable with. That's a great question. I'll repeat the question. The question is, Kafka support key topic where the record for same key goes the same Kafka partition. So with the Iceberg source, how is that handled? That's a great question. So Iceberg do support a partition scheme called bucketing. It's kind of like a hashing. You can send all the records with the same bucket ID, which is basically a hashing function multiplied by number of buckets, to the same bucket, partition bucket. So that way you can group all the records for the same key, go to the same bucket. Then when you read, you can also assign the file for the same bucket to a particular reader. Yeah, so the question is, in the CPU benchmark, the Kafka source 60% CPU usage, and the Iceberg source have 36% CPU usage. Is there why is such a difference? Did we look into that? So I think I did not look into what exactly causing the difference, but I think a couple of things might probably play a factor. Because in the Iceberg source, it's pulling data in a much bigger chunk. Because data come from S3, we get a data file and decrypt them. So it's a much bigger batch compared to the Kafka source read. That's probably one of the reasons. Yeah. But again, I don't want to read it too much to say, hey, Iceberg is more efficient than the Kafka. As it is, I want to say, the point I'm trying to make is as performant as it is.
When you showed the graphs about the spiky lows versus the smoother lows when you went to the smaller intervals, do you run a greater risk of backups when you're shortening the intervals?
Sorry, can you repeat the question again?
In the graphs, you had the smoother graph versus the very, very spiky graphs, and it got smoother as you shorten the intervals.
You're saying, have we go even lower, let's say 1 second commit interval?
Oh, I'm just asking, is there a risk of more backups in the system as you shorten the intervals?
Not really. Well, I think the problem, as we shorten the interval, the problem is the small data files. If we, let's say, commit a data file every second, we're going to only write 1 second of data into a data file. That data file typically to be much smaller, maybe a few megabytes, compared to the ideal data file size, maybe like 100 megabytes we're looking for. So yes, they are producing much small data file, which is the downside. Yeah, that's why we typically don't recommend go very low. That's why I think 1 to 10 minutes commit are pretty common.
Thank you for the presentation. I had one question about the optimization operating to Iceberg based on like the latency of Iceberg itself. You said 10, 11 minutes was optimal interval. Interestingly, you're not considering Flink checkpoints in recoverability, right? Because you mentioned operational costs. The larger the checkpoints, the more costly it will become to maintain this. Can you comment on that?
Yeah, so the question is, earlier we talked about the Iceberg commit interval is 1 to 10 minutes, and that's also Flink checkpoint interval, how fine-grained that is, because depending on how frequent the Flink checkpoint complete, maybe when you have failure, you're going to replay more or less data. So the Iceberg source, Iceberg sync, only commit the data after every successful checkpoint. That's why the commit interval and the Flink checkpoint interval, they're actually identical, they're the same. So I think, yeah, the main thing is you don't want to commit too frequently or to checkpoint too frequently because it can produce small data files. That's related to the earlier question asked, and also too many metadata files. So, but that's why, but you also don't want to commit too infrequent. That can lead to latency and the delay of the data result. So in production, most common I have seen is 1 to 10 minutes. Some people do fast shorter, like every 5 minutes or every 5 seconds or 10 seconds. Some people do longer, like 15 minutes. But 1 to 10 minutes is more common than
maybe I'll ask.
So in the previous presentation given by Sharon, so she talked about the hybrid source, the lambda source, where you read historical data from data lake and latest data using Kafka. So how do you see the pros and cons of purely relying on the Iceberg source comparing with the notion of the lambda source?
Yeah, so good question. I'll repeat the question for the recording purpose. So the question in the previous presentation by Sharon, she talked about the lambda source, where you have old data, historic data in the S3 and recent data in Kinesis. And how is that different with here, I'm talking about with Iceberg as stream source. So as I mentioned in the presentation, Iceberg can use to store long-term data. You can store months, years of data in Iceberg, that's no problem because we put the data in the cloud blob storage like S3. So I think the main problem with that, when you bootstrap, let's say, for 30 days of data, the main problem is actually not to read all the 30 days of data in memory. You want to kind of, using the watermark alignment to process the old data first, then move them along nicely. You don't want to read both new data and old data at the same time. And the other thing with I think, by the way, the lambda source is implementing Flink as a called hybrid source. Actually, my colleague Thomas was implement that. So basically, the key idea with the hybrid source is you finish reading the historical data first, then you transition to the streaming source. But I was just reminded where time is running out. Yeah. Feel free to chat with me afterwards.
Thank you.
Thank you, everyone.